Problem number 4 involves projectile motion, and before we solve that problem we want to review some important ideas in projectile motion. First, we simply drop a ball straight downwards, marking its position automatically every half second with a dot. We see that the spacing between these dots gradually increases, indicating that the ball is accelerating. Next, we fire the ball horizontally with a constant horizontal velocity, again marking the position of the ball automatically every half second. The path of the ball, this projectile, then looks like that. If we draw lines between the vertical position of the ball that is simply dropped and the one that is projected horizontally, we find that at any particular time these balls were at exactly the same vertical position. This indicates that the horizontal velocity of the projectile has not affected its vertical motion. Its vertical motion is identical to balls that are simply dropped. If we also drop lines from the position of the projected ball, we find that the spacing between these lines stays about the same, indicating that the horizontal velocity of the projected ball has stayed constant. In other words, the x and y motions of the projected ball are completely independent of one another. This is an important idea in projectile motion and one that we will frequently use in solving our problems. Next, we review very briefly the equations that we will be using. Here is a typical example of projectile motion, a cannonball shot from a cannon. It rises to a maximum height and then falls back down again. When the ball emerges from the cannon, it has an initial velocity of magnitude v0, which makes an angle of theta with respect to the x-axis. That initial velocity can be broken up into two components, v0x and v0y, which are found in the normal manner. If we examine the projectile at a particular point in its path, say there, let us say that its upward velocity at that point is v sub y and its horizontal velocity is v0x. That does not change, remember, if there is no friction. Let us suppose it is at a vertical displacement y and a horizontal displacement x. Let's further assume that at t equals 0, the original vertical displacement is some value y0, and the original horizontal displacement is 0. Since the vertical and horizontal motion are independent of one another, we can write that the horizontal displacement x at this particular time is equal to the original velocity in the x direction multiplied by the time. The equations for the vertical displacement and the vertical velocity are the same as they were before for free fall. It would be a good idea to copy these equations onto a 3x5 card for reference in doing the problems on projectile motion. We move on now to problem number 4.